that's due on the same day. Oh no, there's not going to be a rubric for the topic map. Basically, I'll be looking at it and just making sure that you have 10 topics on there and that you've made the connections. It's not, I'm not going to be like providing feedback for that. It'll just kind of be like a, did you do it or did you not do it sort of thing. And I guess if you didn't get like full grade, like a full, like pretty much if you do 10 topics and make connections between them, you'll get the I guess you could say 10 out of 10. But if you only did like 7 topics, then I would give you 7 out of 10. So I'll pretty much just give you 1 mark out of 10 for every topic that you include on your topic map, if that makes sense. But I'm not going to follow like a complicated rubric or anything like that for the topic map, just the project itself. Does that make sense? Okay, good. Yeah. Yeah, I think I did mention the topic map in the rubric at the bottom. It says something about like, oh, don't forget to hand that in. Like that's still a thing. But yeah, you're right. We do not need to. Yeah, we don't need to have a rubric for that. Hello, YouTube. Okay. So I'm gonna get started. We're gonna do a couple of things today. We're gonna sort of carry on with our fast forward version of trigonometry. I have in front of me several calculators, and what I want to do is I want to just give you kind of a bit of a rundown of how we use trigonometry in I guess the real world, just really quickly. And how we do it in practice and what it looks like on your calculator. So I want this to be as practical as possible. And I kind of just want to show you just a few little tricks and some interesting points about trigonometry. And like I said, we're going to go very fast. So this is the kind of thing, like I guess this is technically supposed to be a review, but I can't count on it being a review. It's quite possible that you've never seen this before. And also, what else was I going to say? It's important to cover this anyways, but this is probably something that I would normally spend maybe 3 or 4 classes just developing a sense of what trig is and how we use it and that kind of thing. So I'll kind of just show you what I've got set up here in front of me. I went into school, was it yesterday? I think I went in yesterday, yeah. And I picked up a whole bunch of my calculators. So I've got 2 of these kind of graphing calculators. This one actually doesn't belong to me. This one belongs to, wait for it, Miss Bray. Even says so. I stole it from her. Just kidding, I didn't steal it, but I did borrow it. So I've got this calculator here. These 2 calculators are pretty much identical. Well, no, they're not identical, but in terms of the way trigonometry works, they are identical. So they have essentially all exactly the same buttons. The main difference is that this one just has a better processor, but hardly. I mean, like this has a processor of like a digital. This one has the processor for like a microwave, and this one has the processor of like a digital watch. You know, like, and I'm exaggerating. Like, it's obviously a little bit better than that. You can run Doom on these. There's also some homebrew versions of Mario and stuff that you can play on here. But I always forget how to get out of here. Quit. Yeah, so these are good calculators, especially if you're planning on doing applied math at any point. You do a lot of graphing in that class. I think some of the sciences use these calculators a lot. I think that they're grossly overpriced. I find it very upsetting when I think about the price of these calculators. They're very expensive, especially for what they are, in the fact that we live in 2020, and we basically have supercomputers that we carry with us. Like, right, like this thing is way smarter than 100 of these, but this is still like about $100. This is about maybe $70, and that's like used. So yeah, these are the Texas Instruments calculators, the TI-83 plus, the TI-84 plus. I have a video on my website. It's been the video of the week for about 2 months now. I kind of lost motivation to find new videos. But anyways, I've got a great video on this calculator in particular, the TI-83, and just the history of it, and maybe some conspiracy theories as well about it, if you're into that kind of thing. So I'm going to show you how to use trigonometry with these calculators, and then another Texas Instruments calculator. This one is kind of a more reasonable calculator. These are the types of calculators that I would recommend purchasing if you're thinking about getting a new calculator. They're simple, they're cheap, they do everything that you need them to do. The only thing that they don't do is they don't do any calculus, and they don't do any graphing. And that said, I think that they're some of these guys, these sort of pocket calculators, I think that some of them actually sometimes do a little bit of calculus, but I've never been able to get that to work. Like this one here does some sum stuff, like you can do sequences in series on this calculator. But honestly, my general opinion about calculators is that the amount of time that it takes to figure out how to punch some of these complicated things into your calculator just kind of defeats the purpose of using the calculator in the first place. It's just better to solve these problems by hand. I would only ever use a calculator for this sort of thing if the numbers were like gross decimals and I didn't want to have to multiply and divide a bunch of weird numbers, or if there was lots of numbers that you'd have to add. And even then, I would rather just do it on a computer. I would, choose a cool programming language like Python or something like that, Java, or any of the countless useful programming languages that there are, and I would much rather do it on that. So as far as I'm concerned, these sorts of calculators are all that you really need. You don't really need any special functions. The big ones that we're going to be using are sine, cos, and tan right here. So it's a good idea to find your sine, cos, and tan buttons on your calculator. If you are planning on using an iPhone, and I guess I guess I always said, at the beginning of the year, you can't use your phone because you can't use your phone during a test. Well, we don't really have tests anymore, and the final exam, well, like I can't stop you from using your phone, right? Like there's no way I could have done that anyways. So so I may as well just show you how to use it on your phone. So you kind of have to make sure that like on your lock screen that this thing isn't like the portrait orientation is not left locked. So you have to unlock that, and then when you rotate your phone, it'll automatically show a whole bunch of new buttons. And I think it's kind of a similar story for Android, but I stand to be corrected. I'm pretty sure Android lets you take the sign of numbers as well. So there's the sine, cos, and tan buttons on your iPhone. Now, one thing that's really important that we really need to sort out before we move on is just making sure that our calculators are in the right mode. So calculators have different modes. The mode that we want is degrees, because all of the units for all of our angles that we've been talking about, we're measuring them in degrees. Now there are many different ways well, not many, but there's several different ways of measuring an angle. Degree is the one that you learn first. And as you carry on while you study more and more math, you realize that degrees aren't actually the best for measuring angles in all situations. Certainly in most situations it makes sense just to talk about degrees, but in a mathematical sense, we often want to start to think about things like a quarter of a turn or an eighth of a rotation, or you know, 3/4 of a rotation, right? So we kind of think in proportions, and degrees don't really do that for us, right? We have 360 degrees is the full rotation. So I mean, thinking of a half a rotation as 180, like why 180? And if you're curious, the reason, as far as I've been able to tell, the reason why we use 360 degrees is because we have 365 days in a year. And so when they started to use degrees to actually make measurements, they wanted a unit that would closely describe how much a star would change position in the sky after one night, after 24 hours. So if you looked up in the sky and then 24 hours later you did it at exactly the same time the next day, then the star will have moved, and they wanted that to be 1 degree of a one degree. That was their unit. But 365 is not a very nice number. There's not very many divisors or factors of 365, so they decided to make it 360 to make it easier to do operations on, like, for example, making a half of a turn, right? You couldn't even have like a full unit if you wanted to talk about a half of a rotation, if your degrees were measured in 365, right? That'd be an odd number. Already you're missing that factor of 2. So long story short, we need to make sure that our calculators are in the degree mode. And I know that there's always like a setting somewhere on here, and I can never really remember. I think this one is mode right here. No, it's not even mode. Or it's DRG, the DRG button. So you want to make sure that that is in degrees, right? You can kind of see it toggle through 3 different modes. So we're going to make sure that it's on degrees. Now, there's, like I said, there's you could try to find that button on your calculator, and if you can, all the power to you. But because I deal with many calculators, and I don't have just one, I'm usually just using the calculator that's in front of me, and sometimes it's mine, sometimes it's not mine, and even if it is mine, I own about 12 calculators, and I haven't memorized all of their layouts. So what I usually end up doing is, instead of trying to fiddle around, like trying to find like the DRG button or the mode button, what I usually end up doing is I flip it over and I find the reset button, and I get a nice sharp pencil, and I just press that button once, and then it just resets it to the default settings, and degrees are always the default. So it just makes it easy. And also, there are many settings in a calculator that you may not be aware of. And you know, sometimes you leave your calculator on, you don't put the cover on it, you toss it in your backpack, you know, throw it around. They're pretty robust, like they're not going to break. And then all of a sudden, like error 2, and then I've seen it sometimes where it'll give every answer as a floating point variable, which if you know a little bit about computer science, you'll know that instead of the calculator just putting out the number 8, it's going to put out the number 8.0000000, because we're super precise and we want everything to be very precise. So that's what a floating point number is. Yeah. So if your calculator's ever messed up, or if you just want to double check, maybe it's like right before a test and you're like, ooh, I just want to make sure that nothing's going to be all messed up, just hit the reset button. It's easy to find. It's on the back. Not 100% of calculators have them, but every calculator that I've come across has one, and it's just on the back. Reset. Like these are different brands. Like this is Sharp. This is Texas Instruments. I mean, this one's Sharp as well, but like they all have the same button in the same place, and it does the same thing. These graphing calculators, I think they have one too. Maybe not. You know, honestly, I'm still learning how to use this. I never learned how to use this properly, and I'm still learning. Anyway, so that's a little rundown of the calculator. So I'll show you just some of the things that we're going to be doing. So one little trick that we may or may not use today, but just on the topic of calculators, a really handy button to use is this answer button right here, the blue ands. And what that does is it provides your calculator, like your calculator has just a very small amount of memory. And you know what, come to think of it, I think we actually did cover this at the beginning of the year when we did sequences and series. But I'll just remind you that your calculator does have a very small amount of memory in it. So if you have, like if you want to save the number 25, then you can hit 25 equals. And then now it's saying 25 is equal to that. This number is now in our memory. So that means I could do, I could clear this and I could go, it's a blue ands, so I have to hit the blue alpha button. So alpha ands, and then I could just say that's equal to, well, it's equal to 25, of course. Now that's what ands is. So ands is just like the last number that you have in here. Some calculators you can actually get a few variables. You can be like, I'm going to be using this this letter a whole bunch, or this number or this value a whole bunch. Keep it in the memory. I've never really figured out how to do that reliably. Like I'm sure I could figure out how to do it on the Sharp calculator, but then I don't think that this Texas Instruments calculator has that feature, so I don't really bother figuring that out. But just keep in mind that you can do that. The reason that's important is because sometimes we're gonna get we'll have some kind of variable like this, like 3.7 or 5.7, like something that I don't really want to have to write down, but I had to solve for that number, and then all of a sudden I might have to take the sine of that value. So you could do sine and then alpha ands equals, and then there you have it. There's the sine of that value. Okay. So that's a quick little rundown of calculators. The three functions that we're going to be using are sine, cos, and tan. And I say functions in both meanings of the word. Functions as in it's a function of the calculator, and also function as in these are trigonometric functions, like a mathematical function. So basically the way sine, cos, and tan work is that you hit sine, punch in your angle measured in degrees, hit equals, and then that tells you the sine of the angle that you wanted. So we'll do that with sine, cos, or tan. We'll talk a little bit about what those values are, what they mean. I think that we did a little bit yesterday. I just got you to memorize SOHCAHTOA, right? I'm well aware that we're going in fast forward here, but I kind of want to get the ball rolling. So just bear with me here. Another value that we might want is if we already have, if we have two sides of a right angle triangle, you can solve for the missing angle. So the way you would do that is if you had the ratio would be like maybe something like 2/5, right? So maybe 2/5 is the ratio of the opposite side to the hypotenuse. So sine of this right angle triangle would be 0.4. So if I want to undo that, then I can hit the second function and then sine inverse of that, and I can hit answer. So sine inverse of this is 23.5 degrees. Okay. So I'll kind of go back and forth between doing some a video demonstration about what these buttons are doing and that sort of thing once we start doing some problems. But those are the main functions of the calculator that we're going to be using. And honestly, like those buttons that you saw me press here, between that and then using the square root button, you know, if I want to find the square root of 52, that's pretty much all I use calculators for. There's very little. I mean, sometimes if there's a big number to multiply or if there's decimals involved, but there's very few things that I'll actually use a calculator for, right? Like maybe if I have to multiply, like if I'm finding the area of a circle and I want to use pi, and then I would use like 5 times pi. That's a good use of a calculator. But calculators, I mean, in some settings, it's you kind of need to use a calculator a lot, especially in the sciences. But in math, it's like sine, cos, and tan. And even so, in grade 12, you learn how to, you learn some key values of sine, cos, and tan, and you memorize them. And then pretty much all the problems that you see from that point forward have values that you can actually calculate by hand. So so yeah. Anyway, let's take a look at one more thing about trigonometry before we really jump in and get our feet wet. Earlier I set up this little Desmos thing, and I have to change my view. Just one second. There we go. Okay, so now you can see everything. Okay, so here's what the graph of y equals sine of x is. Now I want you to just be aware. I'm not going to ask you to graph this function. In fact, this isn't really a function that we would graph, because usually, like you might notice that the scale is really wonky here, right? So the scale is a little bit strange. Let me steal my keyboard here. Whoops! Shoot! Oh my gosh! My desk is a little bit messy right now. I've got about 100 calculators, a whole bunch of technology. I'm also charging my bicycle lights. I've been trying to go for more bike rides lately, and it's been so hot, so I've been cycling in the evening. And you need lights if you're gonna cycle at night. So I'm trying to charge my lights so I can go for a bike ride tonight. But it just makes for a very messy desk. Okay, almost there. Okay, gotta plug this one in now. Excuse me. I know you guys are just trying to learn some trick here, and I'm getting all distracted by my bike lights, but there we go. Okay, next light charging. Okay, so yeah, what I was saying before is that, oh, and now you can see what I'm looking at. So you might notice that the scale of this is kind of strange. Like from here to here is 1, right? Here to here is 1, right? So this is the graph of y equals sine of x. So that's saying that the biggest value, the largest value of sine of x is 1. You can't get anything bigger than sine of x. And you might say, okay, well maybe if we just keep going. Well, I mean, look at this graph. Like it's very predictable, right? This graph isn't going anywhere. So the largest value that you can get out of sine of x is 1. You won't get any number bigger than that. Additionally, you might notice that the domain of this function, take a look at the domain of this function. The domain is all of the real numbers, right? You can take the sine of any number. Well, what does that mean? Like, let's see if the calculator agrees. So let's try sine of, let's do sine of 900, just a whole bunch of 9s. What's that going to be? Oops, equals, where's my equals button? Sorry, I'm looking at it mirrored. Okay, what? Oh, and look at that. So that is 0.9876883. So that is a value that's between +1 and -1, even though I took the sine of a really big number. So what does that even mean? And that's kind of what I want to start talking about. Like, what is this sine function? What does it mean? Why don't you get values that are bigger than 1 or smaller than -1? And while we're at it, like, what about cos? Cos of x. Oh, okay, it looks pretty much the same thing. Like, well, let's see what's different about it. Let's try y equals sine of x. Looks like it's the same function, just sort of shifted over, doesn't it? Right? So we're going to look at the connections between these two functions. There's also the y equals tan of x. Y equals tan of x. Ooh, look at that. Whoa, isn't that crazy? And oh yeah, I forgot, when this happens, you can't zoom back in. Oh, shoot. Oh, there we go. Okay. What have I done? Okay. And where's my origin? There it is. Okay. So these are the trig functions. This is what they look like when you graph them. and they're pretty interesting shapes. You might recognize them for looking kind of like a sine, or sorry, yeah, like a sine wave, right? I mean, people know. I mean, not everyone, but a lot of you might be familiar with the notion of a sine wave. This is a sine wave. So it's called a sine wave because it kind of looks like a wave, but it's really like the graph of the sine function. And I mean, for all intents and purposes, it may as well be called the cosine function. I mean, there is a little bit of a difference. I mean, I guess the main difference is that the sine function starts at 0, right? And that's kind of a nice place to start, right? It's always nice to start at 0. So that's probably why sine functions are sine functions, because you can kind of imagine like if you're using a sine function to make a sound and you're basically like shaking something really quickly. Well, the way you're shaking like a speaker, right? Like that thing right there. Basically, what's happening is that's shaking, and its position is being described by a sine function. And the reason why we're using sine instead of cosine, so we're using, like we say the word sine wave, we don't say cosine wave, and that's because a speaker has like a resting position, right? And it can go out and in, right? So its starting position is 0. So as you start shaking it, then you start at 0 and then kind of make your way back, right? Anyway, that's kind of what we're going to try to do today is kind of make sense of all of this. We're not going to spend too much time looking at the graphs. So graphing this stuff is kind of a more of a grade 12 topic. So you will kind of look at these graphs in much more detail. You'll also kind of learn how to transform them, just like we were able to with like our quadratics, right? Like you can do like sine of 50, right? And that kind of shifts it over. You could make it taller by multiplying the whole thing by 2. You could move it up by taking the whole thing and adding something to it, right? So let's do +3, right? So you can shift this whole thing around, and there's a lot of fun stuff you can do with these graphs, but we're not really looking at the graphs. I just like looking at the graphs because just looking at the the straight sine graph, it says a lot about the function all at once, right? Immediately we can see that the domain is the real numbers. You can take the sine of any value that you want. And also, it tells you that you won't ever get a value larger than +1 or smaller than -1, right? Those are the minimum and maximum values. And you can see here that you actually do reach -1. You do reach +1, right? Like I got Desmos to sort of point those points out for us just now. You do get those values. So if you looked at the range, you'd be using like the square brackets, not the round brackets. You'd have like the square ones because you would include +1 and -1 in the range. But yeah, so the graph really tells a story here that I think is important to understand right off the hop, because those are some key values, right? So let's start taking a look at how we would use trigonometry in the real world and kind of some of the motivations for it. And I'm just gonna, oh yeah, I gotta change my mouse back here. There we go. And then I'll do this. There we go. Okay, I'm gonna clear some of these calculators away. I think, like, I am going to use this calculator kind of as the guinea pig, but I hope that it's obvious how you would use your own calculator if you're using a calculator that's a little bit different than this. Just one quick note: some calculators, if you calculate sine or something, you have to do like something like 25. Like if you want to do sine of 25, you would do 25 and then hit sine, right? Sometimes you have to do that. I don't know why. I mean, it's what we would call like a syntax thing, right? So it would have a different syntax. So it's basically using a different programming language. In which case you would, instead of writing sine of 25, you might have to do 25 sine. Yeah, you'll just have to kind of figure that out. If you're having difficulty with your calculator, send me a video or something of you pressing the wrong button or something, and I'll figure out what is going on with you, and we'll get to the bottom of it. But it should work. So I am expecting us all to have functioning calculators that can calculate sine, cos, and tan of any value. And our calculators do need to be in degree mode, not radian or gradient. So DEG mode. Okay. So the whole like, not the whole thing, but like the most valuable thing of calculus of trigonometry is to be able to calculate missing sides. And sure, there's some cool puzzles that you can that you can solve, and we'll start off with kind of just like a bit of a puzzle, and then I'll kind of reframe this question in a way that hopefully, can show you that, hey, this is actually like real. Like it's not just, math teachers talking about, imaginary triangles. Like, no, this is a real thing that's used all the time. Like I can't imagine, I literally cannot imagine a world without trigonometry. If we didn't have trigonometry, you could say goodbye to all of technology, like cars, cell phones, computers, processors. Like it's hard to imagine a world without trigonometry. It would be a very different world than what our world is right now. Okay, so here's the thing with trigonometry. So the idea is that often we're given some angle, right? I'm going to say, I think 25 has kind of been the angle of the day. So let's say this angle is 25 degrees, and I know two sides, or no, let's say I know only one side of the right angle triangle, right? Because if we know just as backup, right, just like if we rewind for 2 seconds, if I have a right angle triangle, due to the Pythagorean theorem, if I have two sides, like A and B, I can calculate C using the formula a squared plus b squared equals c squared, right? So what trigonometry can help us do is it helps us calculate the missing sides if we only know one side. But we need to know a little more information, because if you only had like one side and no other information, you can imagine it would be hard to, if not impossible, to determine the length of the other sides. But if you do know one side, let's say that this side is, say, 10, meters, well, that means now we can solve for the rest of the triangle. So the only thing that we needed to know was that this was a right angle, we needed to know that this was 25 degrees, and we needed to know that this was 10 meters. And by the way, it doesn't matter which angle that we know. So maybe we knew this side, or this angle, and maybe we knew this side. The whole point is that we don't need specific sides. It can be any one side and one angle, in addition to the fact that we know that it is a right angle triangle. So given that information, I can calculate this and this. So let's go ahead with this. So remember, sine of theta is equal to opposite over hypotenuse. Cos of theta is equal to adjacent over hypotenuse. And tan of theta is equal to opposite over adjacent, right? So, toa, memorize that. So, let's say we wanted to figure out what this ratio is, okay? So, in other words, like, what if we want to find out what x is? Well, what I'm going to do is I'm going to say, okay, well, what do I know? So I know this angle, right? This is what I know, and I also know this side, and I want to know this side. So in relation to the angle, we have, well, this is the opposite side. This is the hypotenuse. So I have my opposite side, I have my hypotenuse. So SOHCAHTOA, right? We have our opposite, our hypotenuse. So that means that sine of 25 degrees is the opposite side divided by hypotenuse. So that's going to be, oh my gosh, going too fast. Sorry guys. I'm going too fast. Okay, sine of 25 is going to be opposite over hypotenuse. But we actually can't do sine yet because we don't know the hypotenuse. Sorry guys, I don't know why I was thinking of sine. This should be adjacent, right? This is our adjacent side. So goes to show you can still make these mistakes after you supposedly have a deep understanding of this stuff. So this is our adjacent side. This is our opposite side. So what we actually want is tan, because it's TOA, right? Opposite over adjacent. Yeah, pardon my mistake. So tan of 25 degrees is going to be x over 10. And, well, let's just use our calculator to figure out what tan of theta is. Where did my calculator go? I have like 20 calculators. The one that I said I was going to use is now missing. Here it is. Okay, so I'll do tan of 25. Tan of 25 equals... actually, you know what? I'm not going to do that quite yet. First, I'm going to solve for x, right? So solve for x, right? So I'm going to basically multiply both sides by 10. So this is going to be 10 times tan of 25 degrees. And 10 times tan of 25, well, tan of 25 is this thing, 0.46 something. And if I multiply that by 10, so answer times 10, equals that number. So what is that? 4.66. So x equals 4.66, and I'll round, so I'll put the 2 dots on top. So 4.66, and I'll make it look a little bit nicer. And I think we were measuring it in meters. So yeah, great. So you can figure out missing sides of a triangle. And then, of course, now that you know x, you could solve y, right? Because that you could use the Pythagorean theorem for that. Or you could use a different trig ratio. Maybe you could use sine now, because now that you know x, you could do opposite over hypotenuse, because this is actually the hypotenuse. So I just want to quickly talk about like why this is important and why this is the most, like one of the most applied topics in all of mathematics. And I know that I say that a lot about things. I often start a topic like, oh, this is one of my all-time favorite topics. But genuinely, this is one of the most important areas in all of mathematics, just due to the amount that it is applied. So this is applied everywhere. Like you could anything on my desk right now. I couldn't have done it. I couldn't have purchased it. Nobody could have designed it without trigonometry. And look at all this cool stuff on my desk. I've got an Xbox controller. I've got all these lights. Maybe the screwdriver. I feel like maybe the screwdriver could have been made without trigonometry. But you know what? I bet that these little nubs right here, I bet that the machine that used this had a sine function built in, and that's how it was able to sort of like go up and down like that. It was following the motion of a sine function. So pretty much, I mean, the whole, like, the way you can tell with this stuff is anything that like has any kind of rotation, any kind of like rotating thing, or anything that like blinks repeatedly like that. Anything like that it's a sine function, so you can't escape this stuff. Okay, so yeah, so let's kind of, I'm gonna rephrase this problem, and hopefully you can see why it would be important. So like, I'm sure you can imagine that, you know, knowing something like how far away is the moon, like that's a good question to have. Like, it would be great to be able to know that, without having to travel to the moon, right? Like you can imagine that going to the moon is pretty expensive, right? So I wonder if there's a way that you could calculate the distance between the Earth and the moon without actually having to go there. And even if you did go there, like how are you going to measure that? Like are you going to leave a measuring tape at your launch pad and then just like bzzz, like go all the way up to the moon and then see what the measuring tape says? And even if you were going to do that, how long would you know to make the measuring tape, right? Are you going to even have enough fuel to get to the moon, right? It's pretty important to be able to know how far away something is without actually having to go there. And trigonometry can do that for us. So one of the questions that I love to do, oops, not this, in grade 9 when I first teach trigonometry is to take a look at this problem. So, oh yeah, no, I don't want to draw a picture yet. So let's say that we're like on a desert island and there's like food on this island and this is the beach, right? And you want to know how far away that thing is. Well, that would be this length here, right? So you can imagine that like you could, like if you were stranded on an island and you wanted to know like how far away something is, like maybe you know that you can swim 1 kilometer, right? After 1 kilometer, like you're done, like you're gonna drown, but 1 kilometer you can make it, right? So you could ask like, is this 1 kilometer or less, right? Well, what you could do is if you're standing here, right? So kind of the premise of the problem is that you cannot know any information about stuff that's going on over here. Like you cannot cross the beach, right? I mean, you could go a little bit, but like you can't swim very far anyways. So the whole point being that you can't escape the beach. So what you could do is you could walk over like 50 meters, right? And then you could measure the angle. So just sitting here, you could kind of eyeball it and say, okay, well this angle right here, like I don't know what length this is right over here, but you could measure the angle, right? Like you could, like while you're walking on the beach, you can sort of turn, face what you're looking to get to, and then measure this angle, right? So now you know this side, you know the angle. So this would be, well, I'm not going to make the same mistake again. It's going to be tan. So this would be like, if let's call this unknown distance x, right? So x is going to be equal to 50 times tan of our angle theta. So maybe the angle that we measured was, I don't know, maybe it was, let's also just say it was 50 degrees, right? So let's say we've got 50 times tan of 50 degrees, right? Well, let's see if we can swim there. So 50 times tan of 50 equals 59 meters. So without crossing the beach, like without getting our feet wet, we've determined that we can swim there, right? And it's this exact premise that we can do to figure out how far away objects in the sky are to us. Although when it comes to things like galaxies that are really far away, there's not a noticeable enough difference in angle, so we can't use that method, and we use different methods that also use trigonometry, but in kind of more of a light wave, kind of looking at the graph, and we look at it that way. So trigonometry is amazing. Like it's an incredibly powerful tool. So I'm hoping that we're feeling maybe a little more comfortable with trigonometry. I'm hoping that you've done a little bit already and you kind of are starting to remember how this stuff works. But next class, we're going to be looking at something called the Sine Law and the Cosine Law. And they're basically just formulas that help us use trigonometry in an even wider variety of settings. So that's what we're going to do tomorrow. So I know I went over a little bit. Shoot, I forgot to say. I know that we already talked about this in Discord just very briefly, but I did put the rubric up for the final project. there's no rubric for the topic map. The topic map is just the topic map. Just do it. But the project itself, is described fairly well. I mean, the thing is, there's a lot of ambiguity. Like, you can do pretty much anything you want for the project as long as you can email it to me somehow. But the main thing about the project is that you choose 4 topics and you have to demonstrate your understanding of each of those topics. And I've listed the 3 ways that I'm going to categorize your understanding. And they are, number 1, one understanding is you can do some calculations, right? It's like, okay, I can like solve this problem. Give me a triangle and I'll solve for all the missing sides. That's a 1 out of 3. 2 out of 3 would be that you can do these calculations, but you can also explain how they're relevant, and you could explain it to someone who doesn't understand it, right? Like if you had to explain to your peer. So maybe you're making a video or something, and you're kind of doing what I'm doing right now, and you're explaining how it works. That would be a 2 out of 3. And then a 3 out of 3 is to do all of that, so do everything that you did in 1 and 2. But in addition to that, also make connections to the real world and be able to appreciate how this math is useful, and make connections if possible to the sciences, and where a scientist might use this stuff, where maybe someone studying statistics could use this, or maybe even think ahead, like take a look in the Manitoba curriculum. Say, okay, well, I'm going to be in grade 12 next year. What does trig look like in grade 12, right? That would absolutely show. Again, I'm not saying that I expect grade 12 level trigonometry. That's not what I'm saying at all. What I'm saying is, take a look at where we're going with this. Like, what direction are we going with trigonometry? Like, what is our end goal here? So that would be a 3 out of 3. So, and just to be clear, when I say look at the next grade, I'm not saying that I want you to do grade 12 trigonometry. Our focus is grade 11 trigonometry. I want you to be doing this stuff. And that's true with any other subject too. Like if you're going to do rational expressions, do grade 11 rational expressions. Do the rational expressions that I showed you how. But if you want to kind of go the extra mile, then take a look at either the curriculum for next year, like what does it look like? Take a look at maybe how this stuff is used in the field and that sort of thing. So that's how you be marked for each one of those 4 topics you choose. And then there's one more column that I'll use for the connections. And that's just going to be like, what kind of connections did you make between these topics? And again, I describe it in the rubric, but basically a 1 is that you made a few connections. You said, okay, yeah, trigonometry has right angle triangles, and so does the Pythagorean theorem, and there's the connection. Right, and you do that with maybe a few of your topics. Like you just kind of show, okay, yeah, there is some kind of vague connection, and oh, there it is, and you point it out. The second one would be to make connections between all of your topics. So all of your topics, you've looked at them all thoroughly, and you've given me like a whole bunch of connections, and that's great. And finally, to get 3 out of 3, is to take a look at all of the topics that you've chosen and present them in a way that kind of tells a story, right? That there's almost like a narrative to it. So something like, okay, well, I'm going to start with this topic. This topic leads naturally to this topic. And then the topic after that kind of is a combination of the previous 2 topics or something like that. So that there's some kind of, like it's enjoyable to read, right? Or enjoyable to watch if you're making a video. Like make it interesting, right? Like don't just point out the connections because they exist. Choose connections that are interesting and connections that you think lead naturally to the next topic, because all of these topics, like we could boil them down into basically one mega unit if we really wanted to. Like there's a lot of connections to choose from. So I mean, one way you could maybe do that is you could look at one really challenging problem, like a problem from the real world that you need several subjects or several topics to solve completely. Or maybe it's like this one big problem that has sort of several subtopics, and then to solve them all together you get a big thing. That would be a 3 out of 3 for connections. So I know that I'm asking a lot for the connections part. but there's plenty of other opportunity to get rewarded for grades. So, but the 3 out of 3 for connections is going to be hard. I won't lie. Like, you'll really have to work hard to get that 3 out of 3 on the connections. Yeah, so that's how it's gonna happen. Also, don't forget to do the topic map. I can't say that enough. I would start doing the topic map now. Now would be a great time to do a topic map. You know, you can even start it now. Put like one topic down. Write what we did today as just like one little bubble, saying, okay, trigonometry, sine, costan. Just like a little blurb about what it is, and then as we progress and start adding more of the new stuff that we do, and maybe start to cycle back and start looking at some of the other topics that we've covered throughout the year. And you guys are really lucky because you guys have a textbook. My 2 other classes don't have a textbook, so they're going all off of their notes. So you've got a really good resource here. This is a good book, and I mean, I'm hoping that you wouldn't just like copy the table of contents, because I mean, for one, we haven't followed the book completely, like chapter for chapter, section for section. Like, we have skipped some stuff. We've kind of hopped around a little bit, as you know. Like right now we're on chapter 2 or chapter 3. So yeah, I'm hoping that you wouldn't just copy the table of contents, but that's a good place to start, right? To start looking at some of those topics and kind of going through them. Like, oh yeah, we did that, and maybe go to that page and you know, refresh your memory and make a little like a Cole's Notes thing, and then start to think, okay, how's that connected to some of the other topics that I've written down? And I need 10 topics in total. So I've gone way overboard, way over time. So I'm sorry about that. Also, I was watching I was kind of replaying one of the videos from the other day. I forget if it was this class or maybe another class. But the video was chopping in and out. Like, it was kind of choppy. Like, I paused every second. My voice kept on going, but the video itself was like pausing. So I guess I just want to say, if my video feed is you know, kind of acting wonky, let me know. Like, I'm not going to be annoyed by that. You know, like I put a lot of effort into making this like a smooth thing. Like, I really don't want you to get a headache from watching my videos. You know, like, the reason I got this thing is because it's 60 frames per second. There's other ones that are cheaper that are 30 frames per second, but the 60 frames per second is much smoother. Now, I say that, and then I'm just realizing, I think on Discord it's 30 frames, but in any case, you know, the option is there. So if you're feeling nauseous on Discord, then maybe head over to YouTube, because we've got a higher stream there. Anyway, I just wanted to point that out. So yeah, like, if the stream is ever acting out, let me know immediately, and then I'll make sure that I can do whatever I can to fix it. Anyway, I'm gonna go. I'll talk to you guys tomorrow. I hope you guys are doing well. Yeah, I guess, I don't know if you heard, but there's been new regulations on how many people can be outside in a group and how many people can be inside. I think it's like 50 people outside and 25 people inside. So lots of new information to sort of digest and to think about, and yeah, it's pretty interesting. So okay, I'll talk to you guys tomorrow. Bye bye.